In this unit, we focus on the internal network of an autonomous vehicle. In-vehicle network and network are complex due to heterogeneity of devices. The desired features of such systems include real-time communication support, especially for safety-critical applications, low latency depending of application, and flexibility. This example of in-vehicle network depicts the common communication protocols used in in-vehicle network. The FlexRay protocol shown in purple supports both time-triggered and event-triggered communication. It is used in advanced driver assistance systems and anti-lock braking system. The time-triggered Ethernet protocol is shown in red. It is lightweight and cost-efficient wiring and capable of providing real-time communication for advanced driver assistance systems. It is also high immunity to noise and high data rate of up to 100 times that of the controller area network data rate. Another protocol used in the in-vehicle network is the local interconnect network. This protocol is also cost-effective and is often used in applications such as power windows, doors, and seats. The media-oriented system transport or MOS protocol is also shown in the example topology. It is typically used for audio and multimedia communication. The controller area network or CAN protocol shown in green is the most well-known in-vehicle communication protocol. As such, we will discuss this in more detail. The CAN bus was introduced in the 1980s by Bosch. It is a priority-based frame transmission network. It uses serial communication and its single-wire topology significantly reduces network complexity, wiring requirements, and vehicle weight. As can be seen on the figure in the upper right-hand corner, non-CAN-based in-vehicle networks require more wiring. The CAN protocol broadcasts the data on the bus. So, all devices connected to the CAN bus receive every message sent, one bit at a time. It is also easy to onboard new devices to the network during operation. Another important characteristic of the CAN bus is that it provides real-time communication, is deterministic and as a result, is suitable for safety-critical applications such as braking, etc. We distinguish two types of CAN bus depending on bus speed. The high-speed CAN runs at 1 megabit per second and typically connects safety-critical units in the vehicle. The low-speed CAN runs at 125 kilobits per second and is used for low-speed fault-tolerant applications such as passenger comfort. Now let's look at the CAN network in more detail. First, the CAN bus connect nodes, also known as electronic control units or ECUs. An ECU has three main components: an application layer, a CAN controller, and a transceiver. The transceiver provides a few key functionalities. First, digital to analog conversion. It converts outgoing ECU data to electrical signals to be sent over the CAN bus. Next, it also has the capability to convert incoming CAN bus signals to their digital form. Finally, the transceiver provides signal conditioning, which ensures that signals meet CAN bus specifications to minimize signal distortion during transmission. The CAN controller implements the CAN protocol requirements. Specifically, it provides message framing. That is, it prepares the message according to CAN protocol. The controller is also in charge of identifying messages that are relevant to the ECU and discarding the remaining messages. This is known as message reception and filtering. Next, the controller retrieves control and data bytes from the accepted messages for further processing. Last but not least, the CAN controller provides error handling, which is a functionality that has been demonstrated to be a vulnerability in the CAN bus. We look at this in more detail shortly, after discussing the messaging in the controller area network. Together, these components allow the ECU to transmit sensor data, receive control commands, share diagnostic information, and any other functionality added in its application layer. Looking from a security perspective though, ECUs are typically resource-constrained environments, which makes it challenging to implement robust security mechanisms. There are four main types of CAN messages. Data frames are used to transfer data to one or many receiver nodes. Remote frames allow to request data from other nodes in the network. Error frames report errors detected from messages transmitted or received. Overload frames report overload conditions in the network. The figure shows the different fields in a CAN data frame. The first field is a start of frame bit followed by an ID field. This field is 11 bits long in typical CAN messages. Other variations exist with a wider ID field. As we will see in the next slide, the ID field is crucial in determining the order in which messages can be transmitted. The data field is up to 8 bytes in regular CAN frames but can be as large as 64 bytes in CAN FD frames. The data frame is shown in green. The access to the CAN bus is based on the priority of the message being sent. In CAN, the priority of a message is based on the value of its ID field. Because a transmission cannot be preempted in CAN, when a node needs to send a message, it listens to the bus to determine when the last message has completed transmission. This is indicated by 7 end-of-frame bits, followed by a mandatory bus idle time. This idle time is also known as inter-frame space. Once the idle time has passed, all messages that are ready to be transmitted from the various nodes in the network enter into a bitwise arbitration in which the message with the highest priority wins and ultimately transmits all the bits of the frame while other nodes self-suspend transmission. The figure in the bottom right corner shows an example of arbitration. In this scenario, 3 nodes, Node 1, Node 2 and Node 3 enter arbitration. Please note that in CAN a bit with a value 0 is known as a dominant bit while logical 1 is a recessive bit. And, when a dominant bit and recessive bits are both transmitted at the same time by 2 different nodes, only the dominant bit will actually get transmitted on the bus. So, in our example, at times T0 and T1, all 3 nodes transmit dominant bits. However, at time T2, node 3 transmits a recessive bit. Because CAN is carrier-sense multiple access, all devices have the ability on the CAN bus to listen continuously for ongoing transmissions. As a result, node 3 will notice that another node on the bus has sent a dominant bit and self-suspend from the arbitration process. So, from that point on, only nodes 1 and 2 continue to arbitrate. A similar thing occurs at time T3 when node 1 sends a recessive bit while node 2 sends a dominant bit. Beyond this point, only node 2 will complete its transmission. So overall, the ID field with the longer streak of leading zeros has the highest priority and will ultimately win arbitration. This ensures high critical messages always get higher priority. Now let's look at what happens when a transmission error is detected on the bus. Error handling on the CAN bus is handled by the individual ECU controller. The CAN controller maintains 2 error counters for each ECU, a transmit error counter and a receive error counter. Based on the counter values, an ECU can be in one of 3 states: error active, error passive, or bus off state. An ECU is in error active state when both counters are below 128. When one of the counters reaches 128, the ECU goes into an error passive state. When the number of erroneous transmissions keeps increasing and reaches 255, the ECU can go into bus off state, at which point it can no longer communicate on the bus.